Hello students, today we discuss series solution. Usually series solution gives us an approximate solution of given differential equation in series form. Sometimes it is not possible to obtain the solution of given differential equation in the form of elementary function like polynomial or trigonometric function or hyperbolic function or logarithmic or exponential function. So in that case we try to find its an approximate solution, and for that we go for series solution. So before discussing series solution, let's go through some definition. We have a second order ordinary differential equation which is given by y double prime plus px y prime plus qx y is equals to 0. Here px and qx are some function of x. So now we discuss what is an ordinary point and what is a singular point. If a point x is equals to x naught, we have a point x is equals to x naught is said to be ordinary point if these function px and qx are analytic at that point. It means the given point is ordinary point. If any one of p and q is not analytic at this point, then this point is not an ordinary point. In that case, this point is said to be a singular point. And there are two kinds of singular point. One is regular singular point and second one is irregular singular point. One is regular singular and another one is irregular singular. So in what case a singular point will be regular, or otherwise in what case it will be a irregular singular point. So when x is equals to x naught is not an ordinary point, then what we do, we multiply px with x minus x naught and we multiply qx with x minus x naught whole square. And these function x minus x naught px and x minus x naught whole square qx, if they both are analytic at the point x is equals to x naught, then we say this singular point x naught is what? Regular singular point. Very first, x naught is not an ordinary point, it means it is a singular point. And if this singular point satisfy this condition, these both are analytic at x is equals to x naught, then we say x is equals to x naught is regular singular point. Otherwise, if any one of these two is non-analytic at x is equals to x naught, which is a singular point, then that x naught is called irregular singular point. Now we discuss power series. An infinite series of the form summation n vary from 0 to infinity cn x minus x naught raised to power n. Or we can, when we open this summation, we can write it as c naught plus c1 x minus x naught plus c2 x minus x naught square plus so on. So this is called a power series in x minus x naught. And this power series will be convergent, and the radius of convergent is r, where r is what? Limit n tends to infinity cn upon absolute value cn upon cn plus 1, provided this limit exists. So in the interval minus r to r, this series is convergent. Now we use two facts about this power series. First is the power series represents a continuous function within its interval of convergence. It means minus r to r, this power series represents a continuous function. And the second one is a power series can be differentiated term wise within its interval of convergence. Due to these two facts, we use this power series as an approximate solution of given differential equation. So keeping this fact in mind, we can find a convergent series according to a powers of independent variable. X is independent variable, which will approximately express the value of dependent variable. It means in given equation we have y as dependent variable, x is independent variable. So y can be expressed in terms of power series, okay, which contains some powers of independent variable, which is x. Now we go through an example to find which one is the ordinary point and which one is singular point. Show that x is equals to 0 is an ordinary point, whereas x is equals to 1 is regular singular point. So first we write it in standard form, that is y double prime plus py prime plus qy is equals to 0. For that we will divide this whole equation with x square minus 1. Hence we get y double prime plus x upon x square minus 1. This is p. Y prime minus 1 upon x square minus 1. 1 upon x square minus 1 is q into y is equals to 0. Now from here, at x is equals to 0, it will give us a finite value, and similarly q will give us a finite value. It means at x is equals to 0, px and qx both are analytic, and when x is equals to 1, it will give an infinite value. This is also gives infinity. It means we cannot, the p and q are not analytic at x is equals to 1. It means x is equals to 1 is what? A singular point, whereas x is equals to 0 is ordinary point. Now to check this singular point is regular singular point or irregular singular point, for that we will multiply px with x minus 1 and qx with x minus 1 whole square. So we get x minus 1 px is equals to x upon x plus 1, and x minus 1 whole square qx, q is some function of x, is equals to minus of x minus 1 upon x plus 1. This is some function of x actually. So q is some function of x is equals to minus x minus 1 upon x plus 1. So when we take limit x tending to 1, this expression will give us a finite value. Similarly, the second also gives us a finite value. It means they both are analytic. Hence, x is equals to 1, which is a singular point, is now a regular singular point. Now we will discuss how we can find a series solution for given differential equation. So we divide it into two parts. First, if the given point is ordinary point, then we follow different process, and if the given point about which we are to find series solution is, if it is a regular singular point, then there is some different method to find power series solution. So in case of ordinary point, suppose we have the equation number 1, which is y double prime plus px y prime plus qx y is equals to 0, is a second order ordinary differential equation, and we are to find its series solution about an ordinary point x is equals to x naught. Let's suppose that c n x minus x naught raised to power n, summation n vary from 0 to infinity, is a series solution. It means y is equals to this will be a series solution. Now we will differentiate it with respect to x, and we get y prime. Then further we again differentiate y prime with respect to x, hence we get y double prime. Now you put the value of y prime and y double prime in given equation. Hence given equation 1 can be, resultant equation can be termed as a naught a1x minus x naught plus a2x minus x naught whole square plus so on, where this a naught, a1, a2, a's are some function of c's, c naught, c1, c2, and there is some relation between a and c's. So this is an identity, and we equate the coefficient of different power of x equals to 0. So we get a naught equals to 0, a1 equals to 0, a2 equals to 0, and hence from these relation we can obtain the value of c, as a are some function of c. So from here we can find the value of c, and finally we will put the value of c in this equation, which we assumed a power series solution. So in this way we will obtain a power series solution in the case when x naught is ordinary point. So suppose we are going to solve a problem. Here we have x square plus 1 y double prime plus xy prime minus xy is equals to 0. Now we are to find its power series solution about in the powers of x. It means x is equals to 0 is an So first we check that x is equals to 0. We are to find solution in powers of x. It means x minus x naught, where x naught is 0, x minus 0 is x. So x naught, which is 0 here, is an ordinary point. So first we divide the whole equation with x square plus 1 and we get this one. And here this is px, and the minus x upon x square plus 1 is qx, and they both are ordinary analytic at x is equals to 0. It means x is equals to 0 is an ordinary point. So we assume y is equals to summation n vary from 0 to infinity cn x raised to power n. If x naught is ordinary point, we assume cn x minus x naught raised to power n, and when x naught is 0, we assume x raised to power n. So y is equals to y is equals to summation n vary from 0 to infinity cn x raised to power n is a power series solution. Now we have to find the value of c naught, c1, c2, c3, so on. So for that we will differentiate this y with respect to x. So when we differentiate, we get y prime. This, when we expand this series, we can rewrite it as y is equals to c naught plus c1x plus c2x square plus c3x cube. As we studied that two facts, that the series can be differentiated, each term can be differentiated. So when we differentiate it, this derivative of c naught will be 0, derivative of c1x is c1, derivative of c2x square is 2c2x, and so on, 3c3x square, and so on. So y prime is what? c1 plus 2c2x plus 3c3x square, and so on. Hence we can write y prime as summation n vary from 1 to infinity n into cn, when n is equals to 1 into c1 x raised to power 1 minus 1, the first term. When n is equals to 2c2x raised to power 1. When n equals to 3c3x raised to power 2. So this series can be written as summation n vary from 1 to infinity n cn x raised to power n minus 1. So here n is start from 1 to infinity. Here n is starting from 0 to infinity. Now we find y double prime. Now further we differentiate this with respect to x, and we get first term 2c2, second term is 3 into 2 c3x, and so on. This can be written as n vary from 2 to infinity n minus 1 cn x raised to power n minus 2. Now we'll put the value of y double prime, y prime, and y in given equation, which is x square plus 1 y double prime plus xy prime minus xy. Hence we get, after putting it, we get this expression. Here we'll put the value of y. This is y prime and this is y double prime. Now we will simplify this expression. Now there are two terms. First we multiply this series with x square. Second term we multiply this series with 1. This one is third term, this one is fourth term. So there are total 4 terms. So first we multiply 1 with this summation, so we get this one. Now we multiply x square with this one, so here we get summation n vary from 2 to infinity n minus 1 cn x raised to power n minus 2 plus 2, it means x raised to power n. Further it multiplies, so it becomes n cn x raised to power n, this one. Here also this multiplies, so it becomes x raised to power n plus 1. Now what we do here, we will convert all these power as x raised to power n. We write all these power x raised to power n minus 2 in terms of x raised to power n. We will write x raised to power n. This is already written in the form of x raised to power n. Now this x raised to power n plus 1, we will write it in the form of x raised to power n. For that we use some suitable changes, like, so in first expression, first term, this can be written as, for n is equals to 2 into 1 c2 x raised to power 0, 3 into 2 c3 x raised to power 1. For n is equals to 3, it becomes 3 into 2 and for n equals to 4 it becomes 4 into 3 c4 x square. This can be write as m is equals to 0 to infinity, taking this as m is equals to 0 to infinity. So it becomes for m equals to 0, for m equals to 1, for m equals to 2. This expressions can be written as summation m vary from 0 to infinity m plus 2, m plus 1, c m plus 2, x is to power m. Now we can rewrite it as n is equals to 0 to infinity n plus 2, n plus 1, c n plus 2, xn. That is, here what we do, we just replace n by n plus 2. When we replace n with n plus 2, this expression converts into x is to power n. Similarly, here we have n plus 1, so we replace n with n minus 1. So this series will start from n is equals to 1 to infinity. Now we'll put these both series in previous equation, hence it becomes in this way. Now this series is starting from 0 to infinity. This is running from 2 to infinity. It means from here, from this series, if we remove the term n is equals to 0 and n is equals to 1, the remaining series will be starting from 2 to infinity. This is starts from 1 to infinity. It means we remove the terms for n is equals to 1. Remaining terms can be written as a summation from n to 2 to infinity. And similarly from here we remove the term for n is equals to 1. Remaining term can be starts from 2 to infinity. So we write this as 2c2 for n is equals to 0. When we put here n is equals to 0, it becomes 2c2. When we put here n is equals to 1, it becomes 6c3x, and now the rest of terms is starting from 2 to infinity. This is already starting from 2 to infinity. This is starting from 1 to infinity. So for n is equals to 1, it becomes c1x, and rest of the terms starting from 2 to infinity. This is there also we write for n is equals to 1, we get c naught x, and rest of terms starting from 2 to infinity. So taking these four terms together, so it becomes 2c2 plus 6c3x c1x minus c naught x, or this is a term, constant term, this is a term with access to power 1 type term, and the rest of are the terms with access to power 2 type term. So taking these summation together with, we get summation n vary from 2 to infinity. So first term n plus 1 n plus 2 cn plus 2, second is nn minus 1 cn, third is nn ncn, and fourth is minus n minus cn minus 1. Now this is an identity, and we equate the constant term and the coefficient of each power of x equating to 0. So when we equate 2c2 equals to 0, which is a constant term, so from here we get c2 is equals to 0. Now we will put to the coefficient of x is to power 1 equals to 0. It means 6c3 plus c1 minus c0 is equals to 0. It gives us c3 is equals to c0 minus c1 upon x. Now to obtain recurrence relation, now we will put the coefficient of x square equals to 0, x cube is equals to 0, which is a common term. So equating the coefficient of x is to power n equals to 0, we get a relation between cn plus 2 term and cn and cn minus 1. A relation cn plus 2 based over nth and n minus 1th term, where n greater than or equals to 2. As a series starting from 2, this series starting from 2, so this coefficient, this c gives us the value for n greater than or equals to 2. So when we put the value n as 2, we get c4, which is equals to c1 upon 12. When we put n is equals to 3, we get c5. When we solve it, we get minus 9 by 20 C0 minus C1 upon 6. Hence we can obtain the value of C6, C7. Now we'll put the value of C0, C1, C2, C3 in assumed solution, which is y is equals to summation Cn xn. Now as C2 is 0, we'll put 0 here. C0, C1. Now we'll put C3 in terms of C0, C1. We put C1, C4 in terms of C1, C5 in terms of C0 and C1. Now we'll separate this term y is equals to in terms of C0 and plus in the terms carrying coefficient as C1. So y is equals to C0 1 plus 1 by 6 x cube minus 3 by 40 x5 plus so on C1 x minus 1 by 6 x cube plus so on. This is a required series solution about the ordinary point x is equals to 0, where C0 and C1 are arbitrary constant. So in this way we find the solution about an ordinary point in series way. Okay, thank you.